Well, welcome back, everybody, from extended spring break. Hope you've managed to stay healthy. Um, this isn't what I expected to be doing when we got back from spring break, but here we are, and we need to have a successful end of the semester. So let me explain how things are going to be changing. First of all, the lectures will be completely online. What I'm going to be doing is editing together segments from various sources. So this, for example, I'm recording with a webcam on my laptop. Other segments I'll record like I used to do in lecture, just by doing a screen capture of my laptop with my audio. But most of the segments are going to be extracted from videos that I took in 4150 in 2019 and 2018. And I prefer to use those segments because they contain the questions that students asked at the time. And I think that's more closely replicates what it's like to be in class. My plan is to post individual lectures at least one day in advance. And I'm doing that so you can watch them in advance. Because what I'm going to do with the traditional lecture time, which is Tuesdays and Thursdays from 10:45 to 12:05, is I'm going to host a meeting via Zoom where all of you will be able to come to the meeting virtually and ask questions. So it'll sort of be a large group meeting, and you can ask questions about the lecture. That's what it's intended for. And everyone can hear all the answers. So that takes care of the lectures. The problem sets will remain the same, but they'll, instead of being due Thursday and Friday, they'll be due Monday and Tuesday. The consulting hours we're also planning to do on Zoom. We're still trying to figure out exactly how to do it. We'll post details on Piazza. However, the schedule will need to change because the problem set schedule has changed. So we'll be posting a new consulting hour schedule. The final exam, still not sure what to do about that, but I've got a few weeks before that becomes a problem. So we'll figure out how to administer the final exam, but it'll be online in some form. So the remainder of this video is today's lecture. Let me tell you what the segments are. The next segment was inspired because I answered a lot of questions before spring break about the Catice Problem at the time, which was the number theory Catice Problem. And a lot of students were having trouble with understanding the difference between 16 or 32-bit integers and 64-bit integers and double precision floating point numbers. So the first segment talks about that. The second segment that follows talks about this week's Catice Problem, which is the bank queue problem. It basically uses this week's Catice Problem to explain how to, or to illustrate better, how to find solutions, greedy solutions to problems, and how to argue that they're correct. The third segment will be a review of Kruskal's and Prim's algorithm, which we talked about almost 2 weeks ago. You've seen this before, so it'll be a short segment just to get you to remember what those algorithms were. The bulk of the lecture today will be an analysis of the complexity of those two algorithms. And the analysis of Kruskal's algorithm leads to a couple of interesting issues. One is the union find data structure, or the disjoint set data structure, which we'll spend a lot of time today talking about. The other is radix sort, a linear time sorting algorithm. And I'm not sure we'll get to that today. Probably that'll come next time. So we'll take a short break here, and we'll be back with the first segment. When I was helping students before spring break with the Catice Problem, the number theory Catice Problem, I noticed a lot of misconceptions that students have with the difference between int and long and double. It's not surprising that students have these misconceptions because in early classes we tend not to go into the fine points of numeric types. And then in later classes, I'm not sure we say much about it at all. So let me just briefly show you a few things that would be very valuable for you to know. I'm sitting here in JShell, which is an interactive shell for Java. Java has 32-bit integers and 64-bit longs. So if I go in here and I type a number like 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, that's, let's see, that's like 1,234,567,890. Roughly, you can't go over about 2 billion with a positive number if you're using an int in Java. So I'll hit enter and you'll see that it dealt with that number perfectly. On the other hand, if I take that number and I multiply it by 10, I've overflowed the maximum bit length of a double, of an int, and I've sort of wrapped around to negative numbers. I think most people are familiar with that happens. Now, on that problem, everyone knew that they should be working with longs, because I said it in the problem, with 64-bit numbers anyway. So to do that in Java, if you're actually writing a number into a program as opposed to reading it from input or something, a long literal looks like that. So if I enter that, no problem. If I do this, square that number, so I square those two longs, I get an exact answer as well. But if I cube it, it overflows. So even longs can overflow. That's why I made sure, I told a lot of students, I should say, and I said this in class, that you should never, in the number theory problem, if you're using 64-bit integers, never do more than one multiplication before you take a mod to keep the numbers small enough to avoid overflow. Nevertheless, a lot of people multiplied 3 longs like this and then took a mod, and that was the problem with their program. So other students, when they saw they're having trouble with overflow, decided they'd use doubles. So a double is not a good substitute for an integer type. Let me show you why. Let's take this number right here and cast it to a double. Okay? And you might look at that and say, oh, that's fine. We got the exact same number back. And it's correct. That's right in this case. We got the exact same number back. But now let's go here to this number. And cast it to a double. Now you have to look pretty closely to see the difference. So up here is the exact number written as a long. And focus on, we have what happens right here. We get to 5210. Down here we get 5203. So it's off in the last few digits. This final 0 here is missing because of the exponent here. So the thing to know about doubles is, yeah, they can span a really long range before they overflow, but they have a limited number of digits of precision in their mantisses. It's around 16 digits. So if you need more than 16 digits of precision, you won't get it with a double. And furthermore, even for less number of digits, sometimes you won't get an exact representation for an integer. So if you really need integers, which you do in number theory algorithms, you need exact answers. Close isn't good enough. You have to use integer types. Doubles are fine when you're using them to model nature, where getting something to 15 decimal places is always good enough. Encryption won't work if you're only good to 15 decimal places. You have to be good to the last bit. So never think that you just use doubles if your ints or your longs aren't long enough. If you need ints, you've got to use an integer type. All right, so I'd like to talk a bit about the Catice problem that's due next week. if you haven't looked at it yet, it works something like this. You're running a bank, you've got a line of customers, and each customer has an amount they want to deposit, and they have a number of minutes they're willing to wait. If you don't start serving them before that number of minutes is up, then they'll leave. So here's a simple example of the input that the Catice problem would get. So the first line tells us that there are 3 customers, and the bank is going to be open for 2 minutes. The first customer has 2,000 crowns to deposit, and they're not willing to wait at all. If you don't help them right away, they'll leave. The next customer has 1,000 crowns. Again, very impatient. And the third person is willing to wait for a minute before you serve them. So that's the input for that your program would take. And your job is to figure out which people to serve in which order in order to maximize the amount deposited. And all you have to display, though, is the total amount deposited. Now, this one, it's pretty easy to eyeball and see that we should, there are only 2 minutes, so we can serve one person at time 0, another person at time 1. So we should clearly serve the person with 2,000 crowns to deposit at time 0, and then after a minute is up, we can serve the second person with 500. So the output in that case ought to be $2,500. Now, the preferred way to attack the problem is to devise a greedy algorithm for it. And what you've got to do is figure out a rule that lets you look at the available people and pick the right person to serve, and then go on and pick the next person to serve, and so on. So you need to have some technique for making that greedy choice. So let me propose a greedy choice, and let's see how it would work. So my proposal is we're always going to choose the remaining person with the most to deposit. Now let's see how it would work with this example over here. So with this rule, choose the remaining person with the most to deposit. At the beginning, at time 0, we can choose from all 3 people. We pick the one with the most to deposit. That would be this one. And so at time 0, we would serve the person with $2,000, 2,000 crowns, according to the problem. Now, after we've made a choice, we got to narrow down the set of remaining choices because this person here is going to leave. They haven't been served, so they're going to leave. And then the next step is we choose the remaining person with the most to deposit. And there's only one to choose at that point, so we choose that one. So in that case, this greedy choice right here, this greedy choice strategy, gets us the correct answer. Now, think for a minute, pause the video, and think, does this work in every situation? And what I do when I'm trying to evaluate a greedy choice strategy is I try to come up with a counterexample to show it wrong. It's not hard to come up with a counterexample. I'll show you another one here. This one, we've got 4 people waiting in line. One person has $1,000 and is very impatient. $2,000. And $500. So if we apply the greedy choice strategy here, choose the remaining person with the most to deposit, the first person we would pick would be the one with $2,000. At that point, this person would leave. And then we have got to pick in the second round, there's only one person left to pick, and we end up with $2,500 deposited. Well, but if we had chosen a different strategy, we could have chosen the $1,000 person first, and then the $2,000 person first, and just ignored the one with $500, and we would have gotten $3,000 in deposits. So this greedy choice strategy up here doesn't work. So let's try to think of a different strategy. So I'm going to propose this strategy. I'm going to turn the problem around. Rather than choosing the remaining person with the most to deposit and working forward in time, I'm going to start at the end and work backwards. So I'm going to say, from among the customers willing to wait until the current time slot, choose the one with the most money. Okay, so that's just a slight change. It's sort of the same idea, but working in reverse. So let's go back up to this one up here that we started with and make sure that our the greedy strategy still works in this situation. So I'll erase these check marks here. So we're going to run time backwards. There are 2 slots to fill. There's the slot when there's 1 minute and the slot at 0 minutes because the bank's only open for 2 minutes. So we're going to work down this way. And so for this first slot here, we're going to pick from among the customers willing to wait until that time slot. I want to choose the one with the most money. Well, there's only one willing to wait that long. That's the 500 person, and so they get put in that slot. And we ignore them now. We take them out. Now we've got 2 people that are willing to wait to the 0 time slot, and we pick the one with the most. And we get the correct answer of 2,500. Now let's try this one down here with the same greedy choice strategy. Excuse me. So now there are 4 time slots to worry about. We've got 3, 2, 1, 0. So there's no one willing to wait 3 minutes, so nothing to put there. There's no one willing to wait even 2 minutes, so nothing goes there. Now, there are 2 individuals that are willing to wait 1 minute, and we pick the one with the most money. We kick this one out because he's been done. And then the 2 remaining are both willing to wait 0 minutes, and we pick the one with the most money. And in that case, we get 3,000, which was the right answer. So it worked there as well. We can look at one more example. This is one of the examples from the Catice Problem. So we have 4 people. One will wait a minute and deposit 1,000. One will wait 2 minutes and deposit 2,000. Another will wait 2 minutes. And then we got someone with 1,200 that's going to leave right away if not served. So again, we work backwards. We got these time slots to fill, 3, 2, 1, 0. 3, and no one's willing to wait 3, so I'll cross that out. Okay, so we look at the ones willing to wait 2 minutes, at most 2 minutes, and we got these 2. We take the one with the most money, remove them from the list. Now we consider what are the ones that are willing to wait 1 minute. Well, we've got this one here and this one here. Oops, that's incorrect. Let me back up. After we filled that slot at 2, we got to get rid of that one, this one too, because it's not needed anymore. Because they won't wait any longer. So now we got to pick from among those willing to wait for 1 minute, and there's only one of those. And then there's that person we cross off, and then the 1,200. And so we get what turns out to be the correct answer of 4,200. Now, we talked before spring break about how you prove that a greedy choice strategy is correct. So let's try to do that with this greedy choice strategy. And the basic idea is you ask yourself, suppose there's an optimal solution that does not include the greedy choice. is there a way to transform that into a solution that does include the greedy choice? Right? Let's try to do that in this situation. So let me erase a few things here. So let's suppose that we have a problem statement, and we have chosen, let's say, 5 people to fill these 5 slots. And the assumption is that that's an optimal solution. And furthermore, this optimal solution does not contain the greedy choice. The greedy choice does not show up. Let's focus on this last slot right here. Let's say the greedy choice does not appear in that last slot. Well, there are only 2 possibilities. Either that greedy choice shows up elsewhere, or 2, that greedy choice is nowhere in the list. All right, let's deal with it. Let's deal with it in backwards order. Let's say that it's nowhere in the list. Well, I contend that we can go here. This person was willing to wait 4 minutes and is slotted into that spot. Well, we know that the greedy choice, which is not anywhere in the list, was also willing to wait 4 minutes. Otherwise, it wouldn't have been the greedy choice. And it's got at least as much money as this person here. So we take this solution, cross out that, and put the greedy choice right there. We can't be doing any worse. So this must also be optimal. So that takes care of that thing. Now, what about the situation where the greedy choice is somewhere else? Let's say the greedy choice is up here. Could we transform this into a solution where the greedy choice comes last? Well, that's pretty easy. The person that we have in this slot right here was willing to wait 4 minutes, so surely they'd be willing to wait 1 minute. And we know that the greedy choice is willing to wait 4 minutes, otherwise it wouldn't be the greedy choice. So we can do the transformation this way. We'll just take G out of there and that person out of there, and we'll put that person there and we'll put G here. That doesn't change the total at all, so it's still optimal. So any way you slice it, this proves that it's okay to consistently pick the greedy choice according to that strategy right there. And that's a good example of how you go about designing and then arguing about the correctness of a greedy choice algorithm. Before spring break, among other things, we talked about minimum spanning tree algorithms. And at the time, I put off any discussion of the complexity of those algorithms. I want to return to that today. To set up for that, I'm going to go through once again a reminder of what the 2 algorithms we studied were and how they work. So remember, first of all, the minimum spanning tree problem is you're given a connected, weighted, undirected graph, such as the one here on the slide, and you've got to find a spanning tree of minimum total cost. So a spanning tree is going to be v minus 1 edges that connect all the vertices together. If you have more than v minus 1 edges, you're going to have a cycle. And if you have fewer, not all the vertices are going to be connected together. So you've got to have no cycles, v minus 1 edges. Now what we're after is, there are lots of ways to build spanning trees. We want to find one that's of minimum total cost. And so that was the one for that tree that you've seen several times already. The yellow edges form a spanning tree. And the weight of that spanning tree, if you add up the weights, 1, 2, 4, 4, 2, add up all the yellow weights, that's the total weight of the minimum spanning tree, which is 13. Now we looked at Kruskal's algorithm. Kruskal's algorithm, you repeatedly choose the lightest edge that does not create a cycle. So let's animate that. We look at all the edges. The lightest one is of weight 1, so we'll pick it. First edge can't possibly cause a cycle. Now we've got 2 of weight 2. We can pick either one, it doesn't matter. Neither of them forms a cycle, so we'll pick the one from E to F first and the one from C to D second. Now we have the edge from A to D of weight 3. is the lightest edge, but that forms a cycle, so scratch that. Now we've got to choose from among the 1, 2, 3, 4 edges of weight 4. None of them causes a cycle at the moment, so we'll pick the one from C to B. At this point, there are 3 edges remaining of weight 4. The one from A to B causes a cycle. The one from B to D causes a cycle. So the only one we can choose is the one from C to F. And at that point, we're done. All the vertices are connected together into the minimum spanning tree. So that's Kruskal's algorithm. Prim's algorithm sort of works, in operation, it looks sort of like Dijkstra's algorithm. You pick a starting vertex and you grow the tree. What we do is we repeatedly pick the lightest edge that goes from a vertex that we've already incorporated into the tree to a vertex not in the tree we built so far. So we'll start with A. So the yellow vertices are going to be the ones that we've incorporated into our tree. The white edges are the white vertices are the ones that we haven't. So we just pick in this case, we just pick the lightest edge out of A, which goes to C. Okay? Now we've got to pick the lightest edge that goes from A or C to a white vertex. So the lightest edge from a yellow vertex to a white vertex. And that's going to be that edge of weight 2 from C to D. And now D is part of the tree. Now we find the lightest edge, again, from a yellow vertex to a white vertex. And the edge of weight 3 doesn't work because it's from yellow to yellow. So again, it's going to be one of the 4s. It's either going to be the one from A to B, or D to B, or C to F. And we just arbitrarily pick the one from A to B. Again, the only edge of weight 4 here that goes from yellow to white is the one from C to F. And then the only remaining edge that goes from yellow to white is that one from F to E. And then we have found the minimum spanning tree. This leads into discussion of the complexity of Prim's algorithm and Kruskal's algorithm, which I'm not going to do here. I'm going to repurpose a video from 2 years ago. There's Dijkstra's algorithm, we've seen before. Here's Prim's algorithm. So the differences are in yellow. And you can see, the only thing we have in right now, that we didn't have before, is that in-tree array. So we have to keep track of basically the yellow vertices. And we do that with in-tree. And here, we've got to make sure we're not looking at an edge that goes from a yellow vertex to a yellow vertex. And I guess I should have highlighted this difference here too. Okay. And I called one array distance and one array cost. Anyway, there are more differences than are highlighted in yellow, but the major differences are highlighted in yellow. It's a very similar algorithm. Here, the distance is calculated that way, cost is calculated that way. That's the heart of the difference. So what would you expect the complexity of Prim's algorithm to be? It's going to be the same as Dijkstra's. Same data structures, the same structure. So if it's adjacency list, it would be E plus V log V. Okay, but then there's Kruskal's algorithm. Now what is the challenge in implementing Kruskal's algorithm? Yeah?
It's implementing disjoint sets. Which you can
well, but why disjoint sets? What problem do you need to solve to come up with an algorithm for Kruskal's algorithm? What is the greedy choice? Yeah?
Adding edges that don't create a cycle?
Right. We have to be able to identify an edge that causes a cycle or one that doesn't cause a cycle. We've got to be able to tell the difference efficiently. Now, we know how to tell if an edge is part of a cycle. I think that was on the assignment. But it involved the depth first search. We can't afford to do a depth first search every time we're deciding whether to add an edge or not. So, we're going to invent a new data structure called the disjoint set data structure to solve our problem. So, push Kruskal's algorithm on the back burner now and look at this, and then we'll see how it's used. So these are the operations for a disjoint set data structure.
we can create a disjoint data set, and n is the number of elements there are. So what n does is it creates a collection of n sets, each set of size 1, each one contains an integer 1 through n. Okay? So those are, if n is 8, you're going to get the number, you're going to get 8 sets, the first one contains 1, the second one contains 2, and so on. There's a find operation that returns an integer that uniquely identifies the set to which it belongs. Now, for the next few slides, we'll always have find return the largest element in the set. But we'll change that eventually. You just got to be able to uniquely identify it. And then union just combines the two sets to which x and y belong. So let's look at this in action. If we call the constructor, that's what we get. We get a collection of 8 sets. D.find, if we do find of 3, for the next slide or two, we're basically asking what's the largest element to which, in the set to which 3 belongs. Well, this is the set to which 3 belongs. The largest element is 3. It's the only element. Similarly, if we do a find on 5, the largest element is 5. Largest isn't important. We could be smallest. We could do something else. As long as every time you ask, you get the same answer. Okay? Then union. This says, take the set to which 2 belongs and the set to which 7 belongs and put them together. And this says, take the set that 5 belongs to and the set that 8 belongs to and compute their union. How would that change this up here? What's going to happen when we take the union of 2 and 7? Yeah?
2's value becomes 7.
Well, what happens to the list of sets? Yeah?
Gets reduced, 2 and 7.
Okay, so 2 and 7 get smushed together into one set. And the sets for 5 and 8 get smushed together. So you get this picture here. So now you've gone from 6 sets to 8. So the way this data structure evolves over time, as you do unions, you gradually get fewer sets until everything's in one set. Okay? So now we do a find on 3. Let's see. Largest element in that set is 3. We do a find on 5, it's going to return 8. Because that's the largest element in that set. We do a find on 8, we get 8. What if we do a find on 2? You get 7. Okay? Now we take the union of 1 and 7.
So you merge those two sets.
We merge these two sets. We get 1, 2, 7. And then we do the 3 and 4. That puts them together. And, oh wow. Strung a lot together there. But 1 and 7 put these together. 1, 2, 7. 3 and 4 put these together. So you get that. And then we take the union of 4 and 6. That takes the 3 and 4 set and the 6 set and glues them together. So now we only got 3 sets. If we do a find of 3, we get back 6. We do a find of 5, we get back 8. A find of 4, we get back 6. We do this union and that union, and now everything's in one set. So maybe you don't see what this has to do with finding minimum spanning trees, and that's okay. I want to make sure that you've got an idea of what the data structure does. So let me pause here and see if there are any questions. So just those 3 operations. Yeah?
Are the runtime complexities for find, is that n by chance?
Okay, he's asking about the runtime complexity for the find operation. And that's a good question. The way we've talked about it here, this is a very inefficient implementation of the union find data structure, of the discrete set, disjoint set data structure. I will stipulate for now that we can do it in log n time. Find operation can be done in log n time, or n's number of elements. N is the parameter of the constructor. We can actually do better than that. But for now, let's just assume it takes logarithmic time for both union and find. Yeah?
One more question. Would this be back in a adjacency list?
Say again?
Would this be stored in an adjacency list?
No, this has nothing to do with a graph representation. This would just be off to the side. Any other questions? All right, well, let's see how we can use this data structure to implement Kruskal's algorithm. So let's see what we do. We create a new disjoint set data structure using the number of vertices as a parameter. And so we're going to end up, the way to think about it is, you're going to end up with these sets. What will each set contain?
Singletons.
Each set will be a singleton set containing
Yes.
a vertex name, vertex number. So if your vertices are A through X, you'll end up with 24 sets, each one containing one vertex name. Okay? Then you sort the edges by weight. So you take the edges, sort them by weight. Okay? Ascending order of weight. And then our set X is, we're going to build our spanning tree using X. So we start out empty. So then, what we do is we just iterate through all the edges by increasing weight. So we're going to look at each edge one at a time. And then we ask, does ds.find not equal ds.find to v? Okay? So what's going on here? How are we using a union find data structure? What does it represent at any point? Yeah.
Are you saying if u and v are equal on the same set?
Okay, right. So this is saying we're going to use an edge if, let's say you got an edge uv. We're going to add it to the minimum spanning tree as long as u and v, the two endpoints, are in different sets at the moment. So what are we using the sets for? Yeah?
Set membership, two objects are in the same set, there's an edge that connects them.
Okay, if two vertices are in the same set, there is a path that connects them. Okay? So if, as you add edges, the vertices are connected. There are going to be different connected chunks in the graph. So that data structure, the disjoint set data structure, represents the clumps. So initially, every vertex is its own clump. If you add an edge from A to B, then you take A's clump and B's clump and put them together. Now you got a bigger clump. What's going to be the case at the end of this? Is if every time we add an edge, we combine the clumps of the two endpoints. Yeah?
It's all one clump.
We're going to end up with one clump, because at the end, they'll all be connected. And that means there's one clump. So what we do is, if we look at the edges in increasing order of weight, because we want to get the lightest edge, if ds.find of u is not equal to ds.find of v, that means that u and v are currently in different clumps, and it's safe to add the edge. So we add the edge, and then we combine the u and v clumps into a bigger clump. Yeah?
So shouldn't we have an early exit that once we find that we have everything's in one big clump, then we can exit the...
Yeah, we could exit. I mean, it may be that maybe you get lucky and there's a whole bunch of edges, but the first v minus 1 get added. And the rest are a waste of time. So yeah, you could break this loop as soon as there's only one set in the disjoint set data structure, or when you've added v minus 1 edges to x, or any number of things. Okay, so the thing you should picture is the disjoint set data structure is representing the connected clumps that are defined by the edges that we've added so far. Initially, everything is its own clump. At the end, there's only one clump. In the middle, any edge you add has to go from one clump to a different clump. When you add that edge, you smash the clumps together. Now, why are we inventing a new data structure? Why not just use a hash set? Why do we do this? Yeah?
It must be more efficient somehow?
Yeah, it turns out to be more efficient because we're using these sets in a very a different way than you use regular sets. We're not interested. We never look something up and say, is this in a set? We're just asking, are these in different sets? And when we combine, if we use just regular sets for this purpose, it would just be a lot less efficient. So we're sort of creating a custom representation. All right, let's analyze complexity. So look at that and tell me, what's the cost of Kruskal's algorithm? Yeah?
It's E times the cost...
Well, let's take it step by step.
So
What's the cost of that first operation?
it costs V times some constant.
Yeah, so creating the data structure in the first place, it's got to create V little sets. So it's going to be O of V. Okay? What about the sorting the E edges by weight? Well, you've got to get the edges first. That's going to take whatever the cost of enumerating the edges is, that depends on the representation. Plus, then the cost of sorting will be, let's say we do it with merge sort, would be E log V. Okay? Let's see what I got here. So O of nu is the cost of creating the disjoint set data structure. We argued that's O of V. We have to enumerate the edges. We have to sort them. Okay? What else do we have to do?
Then for each edge.
What do we do for each edge? Yeah. This edge will run, this thing runs once for each edge. What do we have to do? How many times do we do a find operation? Twice per edge, right?
So,
So in big O terms, that's just E times the cost of doing a find. And what's the, how many times do we do a union operation?
One per inch.
We do one per edge, or one per vertex rather. And that's the cost. Now we're going to assume that we're using adjacency lists, just to simplify things, and we're going to assume that the graph is connected, so we can simplify it. Okay, where did those simplifications come from? Okay, O of nu became O of V, we already said that. Cost of enumerating a list is V plus E. Cost of sorting is whatever sorting algorithm we use. E find V times union. That's not much of a simplification. So, you know, we throw out the O of V and the O of V plus E because there's E's and V's down here and they're worse. So it's the cost of sorting, E times the cost of find, V times the cost of union. So, let me just do this all out here. So Prim's algorithm, we said, okay, it's Dijkstra's algorithm in terms of complexity. Kruskall's algorithm, that's what we just came up with. We can certainly do the sort in time E log E. And I'll just tell you, you can do the find and the union in each in logarithmic time. So under that assumption, you get, this is the cost of all the union finds. Since the graph is connected, you know that E is bigger than V. Since E is at most V squared, log of E and log of V and log of E are the same complexity. Log of E is at most 2 times the log of V. Anyway, the bottom line is it simplifies to this. O of E times log of V.
it's the same as Prim.
Well, Prim's is, yep, O of E times log of V.
Shouldn't
But,
be V squared for dense graphs.
yeah, I didn't analyze Kruskall's for the dense graph. We can do better. Okay, so this is, I kept promising you we talk about rated sort. So we can improve the bottom line on Kruskall's algorithm by coming up with a faster sort and coming up with a faster union find operations. All right, so we'll take a break and then we'll see how to do that. Okay, so we got 2 things to talk about now. One is, how do you implement disjoint sets? And the other is, how do you do sorting in linear time? Now, neither of these topics has anything to do with greedy algorithms. It's topics that come up because we've been talking about they're sort of necessary to speed up Kruskall's algorithm. So let's look at disjoint sets first. All right, we already saw this slide. That was the example of how a disjoint set works. And we saw that slide too. That's the last slide we looked at. And this is the cost. So we're going to lower this cost by looking at radix sort. We're going to lower these costs by looking at how to implement union find data structure. Okay, so here's the deal. Let's say we want to create a new disjoint set. What we're going to create is 8 trees. Okay? And there we have it. So we're going to represent our sets. Each set's going to be represented as a tree. It's going to be different than trees you're used to. One difference is it's not a binary tree. It could be any number of children of a vertex, of a parent. Okay? In this case, the tree consists of a single root vertex for each set, a single node. And then we're going to annotate the root of the tree by its depth. All right? So all these trees have depth 0. All right, to do a find operation, somehow you've got to find the tree that A belongs to. And then you've got to travel to the root of that tree. And rather than report the largest element in the tree, we're going to report the element at the root. So we'll see later how to find the tree that A belongs to. But in this case, to do a find of A, we just go, we go to the tree that contains A, travel to its root. Well, we're at the root. And we report A as the answer. So we're not reporting the largest anymore. We're reporting the thing at the root. It just has to be consistent. Then we do a find on F, same thing. We go to F, we travel to its root, we report F. Okay? To take the union of two things, what you do is you just have the root of one point to the root of the other. So we do a find on A, we find the root of A's tree, we find the root of B's tree, and then we have B point to A, the root to the root. And why did the superscript on A go up? The depth went up. Okay? So now we're down to 7 trees, and you're starting to see some structure. So here's the other odd thing about these trees. The children point to the parents. You probably used to think of it the other way. But here, we're only interested in we just travel up. Okay? Now we do a union of B and C. Okay? So what are the steps to do a union? Okay? We find the root of the tree to which B belongs. So we go to B, go to its root. We go to C, go to its root. We've done that. And then we have the root of one point to the root of the other. Now, I think we want to keep these trees as shallow as possible. Why do you think it's a good idea to keep these trees shallow? Keep the depth down. Right, the find operation has to travel to the root. So the shallower these trees are, the less work find has to do. So should we have C point to A, or should we have A point to C?
C point to A.
Right, C should point to A, because if we do that, we don't have to change, the depth of A doesn't change at all. What if we'd done the other way? What if we had A point to C?
C's depth.
C's depth would be 2. So how can you tell which way you want to point? Yeah.
Just compare the depth of each.
Right, you compare the depth. You want to have the lesser depth point to the higher depth. And if you do that, if you have one depth that's lower and the other that's higher, and you add that arrow, the depth doesn't have to change. When does the depth go up on one of these things? Right, when you have, like the case where we had A was 0 and B was 0, so you have 2 trees of equal depth. If one points to the other, the depth of the new root has to go up by 1. So we want to avoid that if we can. Okay, let's do a find on C. What would that look like? You go to C somehow. We haven't talked about how to find C. You can imagine there being an array that points up to each of those things. So you find C, you travel to its root, and report A as the answer. So find on C would be A. Let's take a union of E and D. What would happen? Equal weights, equal depths rather.
E points to D.
So E points to D or D points to E, either way. So there's E, there's D. I'll have D point to E. And we'll give it now that the depth goes up because they were equal depths. Okay, union of F and G. There's F, there's G. Just like that. Let's take the union of D and G. You go to D, go to its root. Go to G, go to its root. Equal weight. So one points to the other and the depth goes up. Okay, do a find on G. You go to G, to F, to E. Report E as the answer. So you can see these, it's the find operations that are expensive. Because potentially they start at the, on a leaf and go all the way to the root. What about the cost of a union operation?
It's cost of a find.
Well, the union has to do 2 finds. But then once it's done to finds, the rest is constant time. So really, both union and find have the same complexity because it's a complexity of a find operation. You have a question?
Say we do a find on G, and we find that its root is E.
Yep.
Should we have G just point to E now?
Interesting question. He said, as we do a find on G and we find out its root is on E, why don't we, as part of this, just restructure the tree? We know that G's root is E. Let's just put a shortcut. Take that edge from G to F out, put the edge directly from G to E. What do you think of that?
How costly is it?
That's,
Constant.
it's constant. You know, you're just flipping a couple references.
But if it was a deep tree,
Well, you're doing the work anyway, right? You're starting somewhere, you're going to the root. You now know the root, you know the start. You know, you can just stick in a shortcut. Does that screw anything up? Yeah?
Doesn't that make it so that E has 3 children?
Sure. You can have 3 children. You can have any number of children.
Yeah, but you couldn't have a login like runtime to associate. You'd have more than 2 choices to make.
No, it doesn't matter how many branches are in the tree because we're only ever going from a vertex to the root via straight line. There's no branching you consider. Yeah?
Would you have to fix the levels because F is Z?
Okay, the one price you pay, if we put a shortcut in from G to E, then suddenly, technically, the depth of E is no longer 2 but 1, and the depth of F is no longer 1 but 0. So let me just, long story short, what he just proposed is in fact an optimization that we're going to do probably next time. Okay? That's what makes this even faster. And when we do that optimization, the depths, instead of being actual depths, they become sort of upper bounds of the depth. It's too expensive to fix them up. So we'll use that idea. Yeah?
Why do we care about the depths?
Why do we care about the depths? Okay? Who can answer that question? Why are we keeping track of the depths? Yeah?
When you do your find operation, if it's at the bottom of your tree, you have to travel all the way up to find the root.
Okay. So
I'm just checking that if there's no parent, like why do you need to know how high up you need to go?
when we do a union, we want to do the union in such a way that the depth is minimized. Ideally, the ideal shape of one of these trees is one root that everything points directly to. So just 2 levels in the tree. We want to keep the tree as shallow as possible, and to do that we need to know the depths, so we can have the lesser depth point to the higher depth. Big depths are bad. Okay? What happens when you take the union of H and D? There's H, we found its root. Find the root of D, we go there. Now what will the pointing look like? H will point to E because E has a higher depth. We want to keep it at 2, not make it go up to 3. Pointing the other way, H would become a depth of 3. Okay? We do a union of C and H. So we go to C, find its root. We go to H, find its root. A is depth 1, E is depth 2, so the pointer goes from A to E. Okay, so it's a weird looking tree. E has 4 children. But we never go, you can't go from a parent back down to a child. The pointers don't go that way. Okay? Now, it turns out that this thing I'm calling depth is also called rank. The maximum the rank can get is log n. I'm going to show you why now. But why is that important to know? What does it tell you? If I tell you that the depth of the tree, the depth of the deepest node can never be bigger than log n. What does that tell you? Yeah.
That's the cost of the find operation.
That's the cost of a find operation and also the union operation. We can see that the depth is never more than log n. Then that puts a bound on the cost of the operation. That's before we add your optimization. We add your optimization and make it even better. So let's see why that is. So here's the challenge. I want you to take these 8 nodes and build the deepest tree you can. You can do the unions in any order. You get to pick, but your goal is to end up with a single, you do 7 unions, you end up with a single tree. I want you to make it as deep as possible. So if we were to contrive to make it as deep as possible, what's the worst we could do? Yeah?
The only way you increase levels is by matching same level.
Exactly. The only way the level increases is by matching same level trees. So if we want to have a tree of depth 3, what do we have to make first? 2 trees of depth 2. If we want a tree of depth 2, what do we have to have?
4 trees.
4 trees of depth 1.
Yeah, to make 2 trees of depth 2, we need 4 trees of depth 1. And to make 4 trees of depth 1, what do we need? 8 trees of depth 0. All right? So let's just see how that works. Well, first we'll make 4 trees of depth 1. 1, 2, 3, 4. We do those unions. Now that we got 4 of those, we can make 2 trees of depth 2. 1, 2. And now that we got those, we can build a tree of depth 3. So it took 8 little sets to make one of depth 3. So that's 3 is the log of 8. If we wanted one of depth 4, what do we have to do? We'd have to repeat that. We'd have to have 8 more vertices, 8 more elements. We would do this on those. Now we have 2 trees of depth 3. Then we can get one of depth 4. So the depth, the maximum depth is logarithmic in the number of elements you start with. Now, the optimization he proposed, how would that help? Okay?
Every time you do a find on the maximum depth, you reduce that to just 1.
Okay. So you're doing finds. Even if you're just doing union operations, you're doing 2 finds every time. And so his optimization would tend to reduce, it can't make things worse, and it tend to reduce the depth of the trees. It can't hurt, and in fact, it makes things a lot better. Or better, anyway. Okay, so that's the game we're playing with the disjoint set representation. Now, in reality, you don't need to use dynamic remembering and pointers to do this. You can just do it with a couple of arrays. So I've got that array called rank, which contains the depths. I sort of started out calling it depth instead of rank, but in your book it's called rank. And down here we store the parent. Look at the in between the 2 arrays, those are the indexes. So we're indexed by vertex name. So for every vertex, we know its rank and we know its parent. How do we denote a root? Look at that and tell me how we denote a root. Yeah?
It's a self-loop.
Yeah. So if something is its own parent, that means it's a root. All right, so let's repeat what we just did, but with this representation instead of the one that uses pointers. So we create the new disjoint set, so there you are. Now we do a find on A. So how do you get started with the find operation? How do you find A? Yeah?
Start at wherever you start at A and then go to its parent
Right.
and tell us itself.
Right, so we got the index there. So we just go to index A and we look in the parent array, and there is that. And we notice that we are at the root because it's storing its own vertex name. So that's the find operation. Okay, what about find of F? You go to index F, notice that that's its own parent. Okay, what about union of A and B? Yeah?
F.
Find the root of each,
Right? You find the root of A.
and then
Oh.
you set 1 to be the other.
Okay? So you got to union those 2 things. You notice they have the same rank, so one has to refer to the other. So let's suppose B is going to point to A. What's going to change in my picture?
Parent of B becomes A.
Right? So B's parent will change to A, and A's depth will change to 1.
Right.
Right. Okay? Great. Now we take the union of B and C. So we go to index B, we say, no, B's parent is A, so we go there and we say, oh, we're at the root. C's at the root. We take the union, rank 1 and rank 0, so we want C to point to A. So the entry in C will change to A, and A's rank will stay the same. Rank only goes up when you're unioning things of the same rank. Okay, we do a find on C. We go there. C's not stored there, so we go there. we find A. We do a union of E and D. Well, that's very familiar. There's E, it's its own root, D is its own root. We do the union. D now refers to E as its parent, and E's parent just went up to 1. We do the union of F and G. Okay? Same thing. There's F, there's G, there's the union. We do the union of D and G. We go to D, we go to E, that's the root. We got to find G, so we go to G, we go to F, that's the root. One has to point to the other. So I'm going to have the green one point to the yellow one. So what will be stored at index F of the parent array? E. And what will be stored in the rank for E? 2. Okay? We do a find of G. We go there. That's not the root. So we go to F. That's not the root. We go to E. That is the root. So it's just, again, that find is just governed by the maximum depth of the tree. We take the union of H and D. Let's see. H is its own root. D is not the root, but E is. So what will point to what? H will point to E. So H will, the entry, that yellow thing will become an E, and the rank of E does not increase. And we take the union of C and H. So C, A, that's the root of C's tree. H, E, that's the root of E's tree. So we want to have A point to E, because A has the less rank. So that entry, that yellow thing will become an E, and nothing else changes. And we're done. Yeah.
So rank only half of the rank array ever gets filled, or can even get filled.
Right, there'll be a lot of zeros left.
So is there a way to use less memory?
So we could use, I mean, the best we could do is say half of the memory, but that's just a constant.
You kind of have to know in advance too, which ones
Yeah.
you're going to use.
Well, you could use maybe a hash table instead of an array. I can't imagine that being worth it. Okay, so here it is in code. So we just did the simulation. We got the parent array, the rank array. This guy here just fills in the numbers. Everything's a self loop, all the ranks are 0. Find just iterates until x is equal to parent of x and returns x. So it's just following the numbers, so that's efficient. Union just does the 2 finds, and then what it does, if the 2, what's that mean? If r of x and r of y are the same, how's that going to happen? If x and y are already part of the same tree, there's nothing to do. Otherwise, what you do depends on how the ranks compare. Only in this case, where the ranks are the same, do you actually increment the rank anywhere. Okay? So now we know that this is linear time, this is logarithmic time, that's logarithmic time. And there's a picture that sort of shows both data structures. This is the first one we played with the explicit pointers. That's how you could actually do it. It encodes the same information. And that's the complexity there. Log in throughout. Okay, so before we look at the next slide, are there any, sort of went through here, see what questions I have. Yeah.
Just curious, with the array implementation, how does it know when to stop?
Okay, so he asked, when we're doing this search here, okay, it stops when it finds, let's go forward here. Let's say it's doing a find on G. So G stores an F, they're different, so we go to index F, that stores an E, they're different, so it goes to index E, it stores an E, they're the same. So when it finds that little self-reference, that's when it knows it's at the root. Yeah?
Maybe you already answered this, but why wouldn't you want it so that one node is the parent of all the others?
You would.
You only have one level.
Oh, you would love that. You would love it so that one node was the parent of all the others.
Right.
But it's too much work to get in that form.
Okay.
And so it's too expensive to always keep in that form.
Okay.
The next best thing is to, whenever possible, when it's when you're already doing a find, flatten the tree a little bit as you do it. And so you sort of approach that. You don't quite reach that ideal, but you get pretty close to it. What other questions? There's the complexity. There is, so that's Kruskal's algorithm. So now, this was our thing originally. And at this point, E log V is smaller than E log E, or no bigger, because the trees are connected. The graphs are connected. And V log V for the same reason, since it's connected. So that's our dominant term right there, E log E. And really, what is E log E? Where did that come from? That's the sort. So if we want to make any progress on this, we need to come up with a faster sort. Now, in preparation for the faster sort, which obviously we'll talk about next time, let me tell you a sorting problem that I face. So I give about 4 exams a year, a semester. And so that is 8 per academic year, and I've been teaching for 31 years. So that's almost 250, is that right? 8 times 31? 250 exams I've given and graded. And every time we got to sort the exams at the end. So I've got a class last semester I had a class of over 300. What's a fast way to sort exams? Do we use quick sort? Do we use merge sort? Do we use heap sort? Insertion sort? Yeah?
So you look at the first letter of everyone's name, and then you put them in a separate pile,
Right.
and then...
What we use is called bubbles. It's not bubbles. It's bucket sort. Bucket sort. So essentially, we go into a room with a long table. Me and all the TAs each take a piece of the stack.
Multiple long tables.
Yeah. And we basically just conceptually say, okay, all last names that begin with an A go here, B's, C's, D's, and so on. And we just sort of, in parallel, we're like, okay, Anderson goes here, and Wu goes here, and Smith goes there, and we're sort of dodging each other. Very quickly, we've got our piles into buckets. And that takes linear time, basically. Actually, better linear time because we do it parallel. Then what do? We got the buckets.
And you sort of bucket.
Yeah, the buckets are now small enough typically. Now, when you get to 300, it's starting to push it because it's always the S's that are the problem. And so I've learned to avoid the S's. In parallel, again, we just sort the buckets. Probably insertion sort is what we're doing there. We're just grabbing a pile and sort of rearranging them. And we've gotten it down to the science. We're so good at it now that I don't have to participate anymore. So
You always find something that you got to do. At the
right.
end.
I gotta go to my exercise. Let me just give the final thought is we're going to study rating sort next time, among other things. Counting sort is bucket sort. Also counting. Anyway, bucket sort is sort of the basis of rating sort.